Dr. G. S. Mahalakshmi, Assistant Professor, Department of Computer Science and Engineering, College of Engineering, Guindy, Anna University, Chennai. She has more than 13 years of UG and PG teaching experience and 5 years of research experience. She has so far contributed 85 research publications, and her research interests are Tamil computing, artificial intelligence, text, and web mining. She is an active member in UG and PG Syllabus Revision Committee and designed the syllabi for Anna University and affiliated engineering colleges for the following subjects: Software Requirements Management, Software Quality Assurance and Testing, Artificial Intelligence, Knowledge Management, Object Oriented Analysis and Design, and Tamil Computing. She has also authored several books, 2 journal papers, 31 book chapters, 3 lecture notes, 3 international conference papers, 36 national conference, and 10 other papers. Dr. G. S. Mahalakshmi is an associate editor of Mimanjari, an official magazine on Tamil computing from INFITT. The books of Dr. G. S. Mahalakshmi are Kanithal Adipadai and Kanini Moriyiyal in Tamil language.
Welcome to UGC lecture series in computer science. In the previous lecture, we were discussing about operating system services, hardware, input-output, and the other management activities of an operating system. Operating system does management in 3 ways. Number 1 is storage management, number 2 file management, and number 3 is process management. In this lecture, we are going to discuss about the multiprocessors and the process management activities of an operating system. As an overview, we are going to discuss about the types of multiprocessors, the evolution of multiprocessors, and the relation and comparisons between the master-slave, loosely coupled, and symmetric multiprocessor. Multiprocessing. What is multiprocessing? Multiprocessing is basically a kind of parallelism existing between the processors situated inside the operating system. If there are more than one processor inside the operating system, the processors need to communicate and coordinate with each other for carrying out the fundamental activities of the operating system, such as file management, storage management, and process management. Process scheduling also is an important task in multiprocessor based operating system. Therefore, there needs to be a process manager for managing all of these processors in synchronization. The coordination between every processor is an important activity inside a multiprocessor based operating system. Coordination in the sense, we mean to say that one processor needs to communicate in synchronization with the other processor by sending and receiving messages between the processors needed for performing a particular task inside an operating system. Therefore, there are various benefits of carrying out multiprocessing. The number one benefit of multiprocessing is throughput. Your operating system is expected to provide high throughput and high processing capacity by the usage of more than one processor inside the operating system. There is another problem of multiprocessing. If more than one processors are used, there needs to have a synchronization between the processors, and therefore the speed match between the processors and the commands which are exchanged between the processors needs to be managed by a central authority. The operating system takes care of managing all these centralized activities and brings into execution the concept of multiprocessing in detail. Therefore, multiprocessing helps to increase the computation power for your operating system. And the third advantage is increase of reliability. If one processor fails in doing some job, there is always another processor which is taking care of this job and completing it in the recommended time and giving back to the user. Therefore, no job inside the operating system is failing due to any reasons. The last advantage of multiprocessing is faster processing. Imagine there is one processor doing 10 jobs in an operating system. If you are increasing one more processor inside the operating system, and if you can imagine there are two processors doing the same 10 job, you can correlate the same for two workers doing the same job instead of one worker doing the same job. Therefore, the number of time of executing the entire job is reduced to half than the original. Therefore, increasing the number of processors is said to reduce the processing time, and therefore we recommend multiprocessing. Recommends multiprocessing always goes for faster processing inside your operating system. Here comes a real life example. Imagine there is an order processing going on in a restaurant. You are going and ordering some item, edible item in a restaurant, and think about the processes or steps that are carried off after you order the particular item. Maybe the first one which is happening is the order clerk who is accepting your query. He is basically looking for whether the order is available. Let us assume this as the first activity and the order clerk as the processor 1. So, when the order clerk clears that the requested item is available, he passes on the request to the bagger who will actually carry out the particular task. Therefore, processor 1 can be said as the order clerk and processor 2 can be said as the bagger. Now, there is a message which is sent from the order clerk to the bagger stating that the so and so item needs to be ordered for this particular customer. Next, what the bagger does? The bagger basically searches for the particular item in their database. The item may be printed in their menu list, which the order clerk checks, but the bagger, what he does is he is currently checking the shelf whether the ordered item is readily available for delivering to the customer. So, this is the second activity, and therefore, in this activity the processor 2 or the bagger does the activity on his own. The next activity comes in this way. When the ordered item, say the hamburger, is available readily on the shelf, the problem is the bagger needs to convey it back to the customer via the intermediate person involved, stating that the order is readily available. If the order is not readily available in a cooked state in the shelf, the processor 2, that is the bagger in the real life example, what he needs to do? He needs to check the available raw materials or ingredients to say which are to be selected for preparing the requested item for the customer. Now, this becomes the third activity of the bagger. Therefore, bagger communicates to the cook. When the item is not readily available, the bagger communicates the same information to the cook so that the cook is searching for the raw materials or the ingredients which are to be considered for preparing the particular ordered item. Now, here you can relate this to retrieving the data from the database if it is not in the primary storage. Primary storage, I am relating it to the shelf. If it is not in the shelf, assuming we are going to prepare it for the customer, like that, if it is not in the primary storage, we are going to take it from the secondary storage. This becomes the third activity in the processing example. Therefore, preparing the edible item for the customer needs to be done by a different person involved who is called a cook. The bagger cannot do it. Therefore, like that, you can relate to the real-time operating system example. If this item or if the requested file is readily available in the primary storage, the operating system takes care of the activity, that is to fetch the data from the primary storage to the requested user. which the bagger could be able to do, like fetching it from the shelf directly to the table, dining table. But if the item is not available in the shelf, that is, if the file is not available in the primary storage, the file needs to be searched from the secondary storage and given back to the primary storage, that is loaded back to the primary storage, there later to be used by the CPU. Remember, in the previous lecture we were discussing about the synchronization capacity of the storage device versus CPU. CPU will not be able to communicate with the secondary storage for want of any information. There is a speed mismatch between the secondary storage and the CPU. Therefore, the data or files from the secondary storage need to be moved to the primary storage. There should be some other authority who should be able to do this particular task, like our cook who is going to prepare the item for the particular customer. Next comes another activity. Once the item is cooked, now what the cook should do? The cook should communicate to the other authorities stating that the requested item is cooked and is ready for serving. So like that, the data, once when it is located inside the secondary storage, it can be communicated to the processor 2 requested processor 3 to take the item from the secondary storage. Processor 3 now took the item from secondary storage. It now communicates to processor 2 stating that the item is ready, it is in place for you to take. This becomes the fourth activity. The fourth activity involves a communication back from the cook to the bagger, that is from the processor 3 back to the processor 2. Now we can relate in the activity 2, the bagger failed to identify the item readily available. He communicated to the processor 3. In fourth activity, the communications have been executed and it has been answered in a reply message from the processor 3 to processor 2. Next comes the another activity. Now bagger was an intermediate authority. The person who is actually there to talk or communicate with the customer is not the bagger, it's another person, order clerk, who accepted the order, and there should be another person, cashier, who will deliver the item to customer and get the money instead. Okay, so therefore the fifth activity is passing on the item which the cook cooked to another person who will give it back to the customer. Therefore, there should be another person who is giving back the item to the customer, named the cashier. He will give the item to the customer by getting the money from the customer. So, in operating system example, you can imagine the item is allocated and kept in the primary storage. The processor 2 passes on the data from the primary storage to who is processor 4, to another process which is actually taking care of reading the data from the primary storage and loading it to the CPU. So this becomes the another activity. The last activity is, assuming the order processing example, the cashier has the item which was ordered at hand. Cashier needs to communicate to the customer stating that your item is ready, please pay the money and get back the item. In operating system example, what we shall do? This particular item is capable of this particular processor is capable of loading the requested file into the processor memory, that is primary storage. Okay, so now what this particular processor 4 does, it routes back the request to the original customer. Now who is the customer here? There is a process or there is another job who requested this particular data from the primary storage or secondary storage. Now the entire request has been processed. So finally the CPU is communicating to the processor or job, the process or job or task who has actually initially requested the particular file, and the request has been entertained by now. Therefore, in hotel restaurant order processing, a U relates to the customer. In operating system order processing, this U may relate to a process or task at hand. Now we will go for a break. We will resume to the lecture in a few minutes. Welcome back after the break. We have been discussing the multiprocessors and the synchronization of multiprocessors. Now we are going to continue the types of multiprocessors and how they evolved. Multiprocessors evolved as a support for mid-range and mainframe computers, and later on, due to the reduction in hardware costs, the multiprocessors were also developed to support any common operating system based services. Presently, multiprocessing occurs at three different variations. The number one is job level, second process level, and third is thread level. Job and process and thread are different. You should recollect from the previous slides. The job is basically a particular process in execution in a different area of your operating system, and process is it the same definition holds on, but the process is also the program in execution, but it is also located at the different stage of the operating system process management. And thread is an atomic or indivisible entity of a particular process. Therefore, the multiprocessing occurs at three different levels of the operating system. But in job level or process level or thread level, wherever it would be, there needs to be a synchronization required for managing the communication coordination of all these things in detail. These are the levels of multiprocessors available. In job level, the responsibility which is required is each job has its own processor. All processes and threads are run by the same processor. The synchronization required here is absolutely, there is no explicit synchronization is required, because every job has their own processor, and therefore there need not be a synchronization between the processor. If one processor does more than one job, there needs to be a confusion which might arise, and therefore the coordination required. Here every job has its own processor, therefore job level multiprocessing is not at all said to be a multiprocessing. It is a similar one like your normal running of your operating system. In process level multiprocessing, there are unrelated processes which are involved. Unrelated may be totally independent of each other. We mean unrelated in that way. Therefore, regardless of job, the jobs are assigned to any available processor at hand. Because there is no dependency between the jobs available, the jobs are assigned to different processors which are available readily at that time. There needs to be a moderate amount of synchronization required. Why we say moderate is there is no heavy dependency between the processes, and therefore if one process is delayed for its execution than the other process, it is not at all a big matter. But if there are very little dependency between the processes, some amount of synchronization is required. Therefore, we tend to say that a moderate amount of synchronization is required for this particular level of multiprocessing. The next comes the thread level multiprocessing. Threads are assigned to all the available processors basically here. What is a thread? Thread is an atomic or indivisible entity of a particular process. Therefore, one process may have many number of threads available. Therefore, you can understand one process is not assigned to a single processor. In thread level processing, one process is assigned to multiple processes. How? That is, we do not visualize a process as a process. In turn, we visualize a process in terms of its threads. A process can be composed of more than one thread, or it can be composed of a single thread. Every thread is assigned to every processor. Therefore, there is a heavy dependency between the threads available and which are mounted to the processes. Therefore, because of the high dependency between the threads, heavy synchronization is required between their execution. So, these are the three levels of multiprocessing available and the levels of synchronization required for the multiprocessing. There are three configurations of multiprocessors available. That is, in 3 different varieties this multiprocessing can happen. One is master slave, next is loosely coupled, the third is symmetric kind of configuration. Now let us discuss the master slave configuration. Master slave configuration, to say that there are at least two processors available. One processor is a master processor, another processor is a slave processor. Master processor always give commands and instructions to the slave processor for execution. Slave processor, if it desires to execute a particular process, it cannot do on its own. It has to place a request to the master processor, wait for entertainment of that request. Later on, if it receives a message from the master processor stating that it can proceed, only then the slave processor can proceed. Otherwise, the processes which are bound to the slave processor needs to wait for an unlimited amount of time, because there is a heavy dependency on the master processor at hand. Processes which are bound to the master processor need not wait for anybody else. They can go on their own. Therefore, these are the responsibilities of master processor. Master processor manages the entire multiprocessing. It gives instructions and directs the slave processors to do their jobs. It performs the storage management, file management and process management activities of all its subsequent slave processors. There can be any number of slave processors available in a master slave configuration. This is an example of master slave configuration. Here is the master processor and there is a main memory, and these are the slave processors. In this diagram I have drawn 2 slave processors in here. Therefore, the main memory is basically shared by the master processor and the slave processors. But actually the master processor is the controlling authority which directs the slave processors how to share and what policies to enforce for sharing the main memory. And of course, there are IO devices which are shared only by the master processor. Slave processors send every IO request only to the master processor, and master processor entertains the IO request in detail. This is the setup of a master slave configuration. Now comes the loosely coupled configuration. In loosely coupled configuration, you can actually see the difference between the master slave and loosely coupled. Here there is no master and slave concept, that is, there is no centralized controlling authority. Here every processor have their own memory, their own IO. Processor 2 has its own memory, its own IO. Processor 3 has its own memory, its own IO. But you can see there is an arrow between the processor 1 and 2 which states that a communication and coordination can happen between the processors. The main difference between master slave and loosely coupled is, in loosely coupled there is no centralized controlling. Another advantage is, in loosely coupled there is no heavy synchronization required, because every processor has its own memory and IO. So therefore we call this as independent processing, because every processor have their own global tables. A level of independency a little higher than the master slave kind of configuration. But there are problems in loosely coupled. This high level of independency imposes certain requirements and policies for scheduling the jobs. You can recollect from the slide, if the particular process 1 is going for one type of scheduling and process 2 is going for another type of scheduling, there needs to be a match between the policies of scheduling 1 and scheduling 2. Therefore, if processor 1 needs to communicate with processor 2, the type of scheduling chosen for processor 1 has to enforce a policy match with the scheduling chosen by processor 2. Only then successful synchronized communication can happen between the processors. The problem in loosely coupled configuration is, assuming if there is one process which is going for a failure. You can recall from the diagram, in the middle there was a processor 2. If processor 2 2 fails due to some reasons, there won't be any mechanism from processor 1 to call or reach processor 3. In the example, processor 1, if it wants to talk to processor 3, it talks to processor 2 via processor 2, it talks to processor 3. If processor 2 is going for a failure, now there would be the communication cut between processor 1 and processor 2. This is the only problem in loosely coupled variety of multiprocessor configuration. Now comes the third hybrid variety of multiprocessor configuration, symmetric configuration. Symmetric configuration is decentralized kind of method. That is, there is no controlling authority as like loosely coupled. Here there is a decentralized power which is enforced and executed among all the processors. Here again each processor is should be of the similar type. Processor 1 and processor 2, processor 3, if you are using n processors, every processor should be able to do the same job at the same amount of time with the same policies enforced. We mean to say they should all be of the same family with same configuration. And there is another software kind of requirement. There should be the same similar copy of operating system loaded for all the processors. And of course, every processor have their own main memory and I/O. So we refer to as global tables. As like loosely coupled, in symmetric, every processor has its own dedicated resources. The only difference is it should be of same configuration, it should have similar policies and restrictions enforced, it should have similar operating systems involved. The main advantages and issues of symmetric is over loosely coupled is symmetric is basically more reliable. That is, it uses the resources effectively, because in loosely coupled there was no enforcement on the existence of similar kind of operating system or existence of same family of processor. Therefore, if the configuration of processor varies, of course the policies of the process scheduling will also vary, is also expected to vary. Therefore, in loosely coupled there was a problem due to the mismatch which might exist in the loosely coupled system. But in symmetric, we enforce a restriction on the type and operating system of the processors involved. Therefore, this is of very high reliability when compared to the loosely coupled kind of configuration. The next good advantage is load balancing, that is we call as graceful degradation. Even if there is a failure inside the processors, assuming there is a central processor which is going for a failure, immediately other processors will take over the responsibilities of the processor which was under failure. Because why this is going to happen is every processor involved is of the same type, has the same operating system. Therefore, this can happen immediately. The number one difficulty or the only difficulty for symmetric kind of multiprocessing is it is very difficult to implement it in practical, because the deadlocks can easily occur between the processors. Deadlocks, we mean to say that assuming every processor has one process, 3 processors have 3 different processes, all the 3 processes are requesting the same resource, means all the 3 processors will fight for each other for acquiring the particular resource, and at times this may lead to a deadlock. This is the only problem which needs to be taken care of in a symmetric processing. So this is a symmetric configuration. So the 3 processors which I was discussing, and the main memory and I/O are all shared by the 3 processors, and the global tables are of the same style. Processor 1, how it sees the global table, in the similar way processor 2 sees, in the similar way processor 3 sees. There is no hidden information between the processes. The only problem is if everybody is requesting the same type of resource, deadlock can happen. Therefore, there needs to be a high synchronization required to manage the processes involved in symmetric multiprocessing. But this is said to be the most efficient way of process management. These are the challenges in symmetric configuration. interrupt processing is one particular challenge. That is, if one process is getting an interrupt, if the interrupt needs to be entertained, other processes has to be updated regarding this particular interrupt, because everybody are sharing the same resource, remember. So interrupt processing is the number one challenge, and there may be more conflicts arising due to the sharing of resources. So, and the third conflict is synchronization between the processes, which we were discussing in the previous slides. And the next most important activity of operating system is managing the memory. So all data in memory before and after the processing needs to be taken care of, needs to be stored or retrieved effectively in the correct manner. This is one important challenge or one important service of your operating system. And apart from data, all instructions also needs to be balanced and managed inside the memory for their successful execution. Therefore, the objective for memory management is to utilize the CPU in an optimized, effective manner to deliver the user's request at the desired amount of time. So these are the basic activities of memory management. Keeping track of which parts of memory are used by whom, that is by which process, which are not used, and deciding which processes involve the movement of data, and the third one is allocation of memory and removing of the contents from the memory, which we say as reallocation or deallocation. These are the activities of memory management. Next comes the service of operating system. This is storage management. Managing the storage is another responsibility of the operating system. Allocation and reallocation of the data is another activity of memory management. Now comes the next important activity, storage management. The parameters which needs to be taken care of here is the speed, access speed of the device, capacity of the device, data transfer rate, and method used to move the data to and fro the I/O device. These are the important things which needs to be taken care of in storage management. In file system management, there are various things which are done by the operating system. That is, creation of files, deletion of files and directories, and the methodology to handle the files and directories, and mapping the files to secondary storage and mapping them back again, and taking backup when needed. In mass storage management, usually the disks used to store data that does not fit in main memory, or data must be kept for a long period of time. Therefore, the OS is involved here for managing that kind of data. The speed hinges on the disk subsystem, and the efficient algorithms used are of central importance in mass storage management. Therefore, the main activities in mass storage management is managing the free space and allocating the data or allocating the files to the storage, that is storage allocation, and scheduling the disks in the efficient manner, which we call as disk scheduling. In mass storage, therefore, there is some important thing which needs to be told here. There is a write once read many called WORM and RW, which we call as read write. These two different policies needs to be managed in an efficient manner for managing the mass storage effectively. In summary, we have discussed the definition of multiprocessing, the responsibilities of a multiprocessor, the types, evolution and levels of multiprocessor, and the configurations of multiprocessors. We have also discussed in detail the configurations of multiprocessors as master-slave configuration, loosely coupled configuration and symmetric configuration, and the dependency between every configurations. And we have also discussed a short review about memory management, storage management and file system management, and the parameters which needs to be examined for managing the files into the operating system. Now let us discuss few questions about multiprocessing and file storage management. Question number 1. How are the files stored actually? Question 2. How does the operating system manages the free spaces in disks? Question 3. Why is intelligence needed for allocation and reallocation? Question 4. Why is prefetching needed? Question 5. What is swapping? When is it actually required? With this, we come to the end of Introduction to Operating Systems. We have actually discussed about the definition, services and responsibilities of operating system in terms of file storage, mass storage, process management and the varieties of multiprocessor, multitasking and multiprogramming involved, with an eye on the optimism which needs to be taken care of by an efficient operating system. Thank you.